Hello, my name is Ethan Mook, and welcome to my talk on doubly efficient private information retrieval and fully homomorphic RAM computation. This is joint work with Wei-Kai and Daniel Wichs. I want to start off the talk by giving a bit of a motivating example. And so for this, we'll consider the problem of Google search. So in this problem, we have Alice as a client on the right-hand side, has some query that she wants to make to Google, and she will get back a set of responses exactly as you would normally expect. And the question that we want to ask is it possible for this Google search to be made fully private? And what we mean by this is that Alice is able to encrypt her query in some manner and send it along to Google, and Google does some computation and is able to send back an encrypted version of the response that Alice can then decrypt and use exactly as normal. And however, throughout this process, we want that Google to learn absolutely nothing about Alice's query. And this problem can be seen to be solved by this extensively studied and very powerful tool of fully homomorphic encryption. And essentially what this gives is a way for Alice to encrypt her query, and Google is then able to evaluate some arbitrary function on Alice's query, on the encrypted version of Alice's query, producing an encrypted version of the response. And so this seems to almost exactly solve the problem that we want. However, there's a major caveat here, and that is that all FHE that we know of operates in the circuit model. And kind of the reason for this is that we don't have a mechanism to make efficient memory accesses while simultaneously preserving the security of the computation. And what this means in our setting, or the setting of this motivating example at least, is that Google would need to read the entire content of the internet in order to answer each encrypted query. And for a company at the scale of Google, this is obviously untenable. And so the question is whether we can do better than this. And the answer after this work is yes, we can do better, and we build an FHE scheme that works in the RAM model of computation. And what this will look like is that Google will first pre-process the internet into some specialized data structure, and afterwards, and this is a one-time cost, and afterwards it can answer any future encrypted queries by only accessing a few locations in this data structure and run in nearly linear time in the standard, or in what Google would have done with no security. And so just to give a bit of a formal definition for FHE, this setting, we have a client that holds a private input X and a server that holds a public input Y. And together, we want that at the end, that at the end of running some protocol, the client, Alice, is able to learn the output of an arbitrary function evaluated on the two inputs. And so the way this will work is Alice will sample some key and encrypt her input. Meanwhile, the server thinks of the function as some circuit and can then evaluate this circuit on Alice's ciphertext, producing a new ciphertext. And the ciphertext has the property that if you decrypt it, it is under Alice's key, it will give you exactly the output of this function evaluated on the two inputs. And this is in, FHE is this very well-studied object, and it has these wonderful security and efficiency properties in the sense that the server, throughout this protocol, learns nothing at all about X. And the client's time and communication are completely independent of the size of the circuit and of the size of the server's input Y. And however, the big downside here is that since we're working in the circuit model, the circuit time is at least linear in the circuit size because it must evaluate the circuit. And since the circuit takes as input Y, the circuit will necessarily at least be the size of Y. So it must be at least linear in the runtime of Y. And so what we want to do in the setting of RAM-FHE is build a scheme that is almost identical to standard circuit FHE in the way that we use it. That is, Alice will still sample a secret key and encrypt her input X, and the server will still run some eval function to produce a new ciphertext. And we want the exact same we want the exact same security property as in Circuit FHE, and we want the exact same client efficiency properties. However, we will now also enforce that the server runtime should be nearly linear in the RAM runtime of the program that is to be evaluated on the two inputs. And for a reason that I'll explain a bit later in the talk, we can't actually do this unless we additionally allow the server to pre-process the public input Y in some offline pre-processing phase that is done once. And then, and we hope, and we will, this pre-processing time should take nearly, should be almost linear in the size of Y. But then after that, all future queries can be done in time that is almost linear in the RAM runtime. And so you can kind of think of RAM-FHE as having like these three settings in which it would have advantages over Circuit FHE. And so in the first case, like this is, you can imagine this as the case of Google search. If the input Y is very large and the client makes some like small queries, the RAM-FHE could have an advantage over Circuit FHE in the sense that a RAM program can run in sublinear time in its inputs, and so therefore the server cost of evaluating the Google search algorithm would be much smaller under RAM-FHE than under Circuit FHE. Similarly, our scheme is able to handle the setting where there is a large private database that may be outsourced to the server. So maybe Y is empty in this case. And if this, the circuit in Circuit FHE, evaluation would have to be at least linear in the size of Alice's private input, but in RAM-FHE it can be sublinear. And even in the case where X and Y are both short, or the runtime is at least linear in both of them, there is still like this quadratic overhead in converting a RAM program, which is our natural notion of computation, into a circuit. And so therefore, it's potential that RAM-FHE could have advantages over Circuit FHE, even in the case where X and Y are short. Okay, and so the first evidence that RAM-FHE was possible was given in 2019 in a work due to Holmgren, Hamlin, Weiss, and Wichs, where they built a weaker version of RAM-FHE, a version where there's no public input Y, and they base it on heuristic assumptions of like heuristic use of ideal obfuscation, among other very strong tools. And in contrast, in our work, we build RAM-FHE based on a standard assumption, the ring learning with errors assumption, together with assumptions on circular security of an FHE scheme, which is a standard, which is known to be, or which is essentially required in all FHE constructions. And just to comment on this assumption, Ring LWE is really a well-studied and is a relatively standard assumption, and it has been linked to worst-case problems in ideal lattices, as well as, and it has been the basis of some of the new NIST standards on public key encryption. And additionally, we also give alternate constructions based on some other assumptions, but we'll focus on Ring LWE for this talk. And so, the main challenge that we overcome in building RAM-FHE is that Circuit FHE doesn't give you any mechanism to make any efficient database access under FHE without revealing the access pattern. And so truly the main challenge will be to hide the access pattern that the RAM program makes throughout this homomorphic evaluation. And so in view of, for the purpose of this talk, we're going to focus on a simpler problem that is private information retrieval, which is really about solving this problem of making efficient database queries while hiding the access pattern. Okay, and so the setting of private information retrieval is that there is a server that holds some large database, and a client holds a location, like an address in that database that it wants to access. And so they want to run like a simple two-run protocol, and the goal is that the client can retrieve the database, like the value located at the chosen at the chosen location without revealing the location that she cares about. And so, without any efficiency guarantees at all, there's a trivial solution here where if the server sends the database entirely along the internet to the client can essentially just look through the entire database and find the one location that she cares about. However, obviously this is unsatisfying, and so it has been known and it's been well studied that using crypto we can get that the client's runtime and the communication are both polylogarithmic in the size of the database using just a 2-round protocol. However, there is this same kind of caveat that appears here. And the caveat is that the server always reads the entire database during the protocol. And so this would imply that the server's computation is always at least linear in the database size. And it turns out that this is actually inherent if the server only stores the database. And to see why that is, there's like a very simple lower bound here, where if the client intends to look for the value at index I and sends like some query corresponding to this index, and the server is able to answer this query while reading from the database, every location except for some location index j, well, the server will necessarily have learned that I is not equal to j, because the server didn't even access the value at location j. And so, because of this lower bound, it is impossible to achieve a version of private information retrieval where the server holds, where the server just stores the database and also runs in sublinear time. And so, the setting of doubly efficient private information retrieval is trying to get around this lower bound by having the server, instead of storing just the database, the server will pre-process the database in a one-time offline pre-processing step into some new data structure, which will denote db tilde. And then afterwards, the client can then make queries that the server can answer only reading some small number of locations from the data structure. And so in this sense, doubly efficient PIR is capturing the main challenge of building RAM-FHE, in that it's the question of hiding the access pattern, like where I'm reading from in the database, while allowing the server to do this in a way that is very short, or like takes very little computation time. And so doubly efficient private information retrieval was originally proposed in the year 2000 by work of ASHE and Malkin, but they gave no evidence that this was possible. And the first evidence actually came due to 2 works in 2017, where they construct a weaker notion of DEPIR, which is called keyed DEPIR. And in this setting, there is a trusted third party that does the pre-processing and computes this data structure, db tilde, and then distributes db tilde and a public key out to the server and all the clients. And moreover, the constructions of this keyed DEPIR notion both relied on some new and non-standard cryptographic assumptions, as well as heuristic use of obfuscation. And in contrast, in our work, we get an unkeyed notion of DEPIR based only on the Ring LWE assumption. And so first, what do we mean by unkeyed? In unkeyed, we have there is no trusted third party. Instead, the server deterministically computes the pre-processing on its own. And then later, as with any normal PIR protocol, the client can query the database in a simple 2-round protocol that will have sublinear runtime for both the client and the server. And so just to state what efficiency we actually get, so for any epsilon and any database of size n, the preprocessing runtime is nearly linear in n, so it's n to the 1 plus epsilon. And so that includes the size of the data structure that the server will store. And the online runtime of the protocol is polylogarithmic in n for both the client and the server. In addition, we also develop a notion that we call updatable DEPIR, where we give the client the ability to make public updates to the server, and this can be done in sublinear time. So essentially, we don't have to recompute the data structure every time. However, there's no security guarantee on these updates. And additionally, we also get an alternate notion of like an alternate setting of efficiency parameters where we kind of have the ability to trade off by reducing our preprocessing time and size while paying for more in the online phase. And so, so now to discuss exactly what our techniques are, we our template for going forward is to essentially combine two different things, like two different objects. The first is we will construct a simple PIR from homomorphic encryption, and we will combine it with an algorithmic technique that allows us to pre-process polynomial evaluation. This is due to Kedlaya-Umans in 2008. And these are two actually relatively simple objects, and we're going to combine them, and our main contribution is kind of getting these things to mesh well together in a way that will play nice, because they each have some set of constraints that they'll put on the actual on the parameters that we're allowed to choose and so forth. And just looking ahead a little bit about what we'll need to do, what we're actually going to use is we're going to use a notion called somewhat homomorphic encryption, which is slightly weaker than fully homomorphic encryption, in the sense that we can only evaluate low-degree functions on the inputs. And then, looking forward, the reason that we'll want this is ultimately we're going to try to use this this system of polynomial preprocessing, which has this algebraic structure to it, and all ways that we know of that give fully homomorphic encryption kind of fundamentally rely on some non-algebraic manipulations to be done. And so instead we're going to look at a somewhat homomorphic encryption scheme. And so the way this basic PIR from somewhat homomorphic encryption will work is Alice will first write her index I in base D. You can think of D as 2 for now, but we'll set D later. And then, meanwhile, the server will view the database as a polynomial over ZD, where evaluating it at the base D decomposition of an index I will just produce the database at this the database value at this location. This can essentially be formed just simply by interpolating over the database. And we'll note that this FDB has is a database or is a polynomial that has small individual degree, and its total degree is at most d times m, so it's d times log log n. And so the way that this protocol will work is Alice will first sample some secret key and send over encryptions of each of the base D digits of her desired location, and then the server will simply just use the SHE to evaluate this relatively low degree function on these encrypted digits, producing the database value that Alice can then decrypt. So assuming that we have an SHE scheme that works for large enough degree, which this degree D is relatively low, this will yield a simple PIR scheme, but it does not have the efficiency property that we want yet. Evaluating this function takes at least linear time in the database size. And so that's where our the preprocessing technique will come in. So we use this result due to Kedlaya-Umans in 2008, where the result is that if you're given a polynomial that is m-variate over a ring ZQ, that has individual degree at most d, we can pre-process this polynomial, given the coefficients of this polynomial, we can pre-process it into a data structure and afterwards quickly evaluate it on any point in ZQ to the m. And so we note that the total pre-processing time is n times an m to the m term, and the evaluation time can be viewed as has relatively low evaluation time. And in fact, this system of preprocessing works over even larger rings than just ZQ, and that will be important for us later. but and ultimately, like, we want to set parameters such that the data structure is only slightly superlinear in the total number of coefficients in F. And so what we'll need is, since we have this m to the m term there, we need to set m to be like sub-logarithmic so that we get a only slightly superlinear blow-up in the pre-processing time. And so we'll choose parameters. We'll set d to be, like logarithmic in n, and m will then be like log base d of n, which is like log over log of n. And so using these, given this choice of parameters, we get that the total pre-processing time is roughly n to the 1 plus epsilon, and then the evaluation time is polylogarithmic in n. And so now the question is, like, given what we know, can we now just simply plug in the KU08 preprocessing scheme to our basic PIR? And the answer is not quite yet. And the reason for this is that there's still like this SHE eval function, which the server is not directly computing the polynomial FDB. Instead, it uses this SHE eval function that may not actually be polynomial computation. And so what we want is a scheme, or an SHE scheme, where evaluating a polynomial is exactly equivalent to evaluating a polynomial over the ciphertext is exactly equivalent to evaluating it over the plaintext. And so that's exactly what we asked for. So this is a notion that we introduced called algebraic somewhat homomorphic encryption, where in this setting there is like a plaintext space, which we'll think of as ZD, and encryption maps plaintext messages to ciphertexts that are in their own ring, or their own space that has a ring structure on it. And what we'll require is that addition in the ciphertext ring directly corresponds to addition of the plaintexts in the plaintext space. And similarly, multiplication in the ciphertext ring corresponds to multiplication in the plaintext space. And so what this means is that the ring operations that we do in R, the ciphertext space, are exactly computing the evaluation of over ciphertexts. And so like there's no explicit eval function necessary. And so this can then be extended to polynomial evaluation over ciphertexts by simply just evaluating a polynomial over ZD can be equivalently done over ciphertexts by first lifting this polynomial to be a polynomial over the ciphertext space. And since we're in the land of somewhat homomorphic encryption, we allow kind of everything to grow with, like, there will be a total degree of the polynomial that we will be willing to evaluate, and all of the complexity of all of the bit size of the ring elements and the decryption and encryption time can all scale as a function of the total degree that we care about. And it turns out that getting ASHE is really something that has already been done, because many of the earlier examples of attempts to get FHE actually went through a system that had this sort of algebraic structure to it. And really, like the only difference here is that, like, in their old setting, they were trying to reduce the growth of noise so that they could ultimately get to a fully homomorphic encryption. However, in our setting, we're willing to accept the amount of noise as long as we preserve this algebraic structure. And so, there are only making minor modifications to prior SHE schemes yields exactly this algebraic somewhat homomorphic encryption that we care about. And so there is a work due to Brikursky and Vaikuchanathan in 2011 that builds ASHE based on Ring LWE. And that is the main construction that we use in this paper. And so we get, using an ASHE and combining it with the KU scheme, exactly our final DEPIR construction, which essentially the server will first compute this polynomial FDB and lift it into the ciphertext ring, and then preprocess that polynomial using the KU08 preprocessing. And then evaluating this polynomial over ciphertext will directly correspond to evaluating the polynomial over plaintexts. And so therefore, the server's runtime can be sped up by the preprocessing of like the preprocessing scheme, and while preserving the ultimate correctness of the basic SHE based PIR. And so this is our final DEPIR construction, and this is everything that we do. And so now, just before I wrap up, I want to give a bit of a taste of what we do to upgrade our DEPIR to use like the techniques from our DEPIR to build a RAM-FHE. And kind of at a very high level, what we do is we'll use the ASHE structure of our DEPIR to kind of glue it together with a suitable circuit FHE scheme. And then we'll use like this FHE scheme to do some parts of the computation, and then switch to DEPIR mode when we want to access memory and kind of switch back. That's kind of at a very high level what we do. I'll refer everyone to the full paper if you want all the details. But kind of suffice to say, based on our DEPIR, we build a RAM-FHE that has the following parameters. That is, like the preprocessing time is nearly linear in the public input y. It has the same 1 plus epsilon loss, or like overhead. And the client time and communication are nearly linear in just the size of the client's input and the output of the computation. And the server runtime, like the evaluation time, is also nearly linear in the total RAM runtime of the computation. And so to conclude, we construct DEPIR and RAM-FHE based on the Ring LWE assumption. And to, so there are a number of open questions that are left after this result. First, like, there are myriad possible directions you can go, thinking about applications of DEPIR and RAM-FHE, like of the objects themselves. Like RAM-FHE is this very powerful tool, or maybe just the techniques of using Kedlaya-Umans preprocessing. There are potentially many applications of this. One other very pressing question I think is interesting is, can we do this from plain LWE rather than from Ring LWE? And then finally, can we do this in a way that does better in terms of practical efficiency? As it stands right now, our construction is definitely not practically efficient, but it does appear that there is hope there for better practical efficiency, and because there are actually a lot of knobs to turn, both on the ASHE side of things and on the Kedlaya-Umans side of things, and together these present some amount of hope that the DEPIR could end up being practically efficient. And this concludes my talk. Thank you for listening.